Hi, my name is Matthew, and I am a teacher candidate in the UBC B.Ed program. In this video, I'm going to be discussing the use of pulleys to create a mechanical advantage system that reduces the force needed to dislodge a boat that has been wrapped around a rock in a set of rapids. One principle that is essential to understanding how mechanical advantage works is the principle of conservation of work throughout a system. Simply put, the principle of conservation of work states that the work put into a system by the effort, or the applied force, must be equal to the work done by the system on the load, or the object being moved by the system, if no energy is lost to the environment. Work is defined as the product of the force along an object's direction of motion and the distance moved by the object. This can be written in the form of an equation as W equals F times D, where W is the work done on an object, F is the force along the object's direction of motion, and D is the distance moved by the object. If you do a unit analysis of this equation, you'll find that the units for work are joules. This makes sense because work is a measure of the change in energy of an object. In the equation shown on the screen, you'll notice there is a subscript on the F. This subscript indicates that the only component of force that contributes to the work done on an object is the force parallel to the object's direction of motion. Mechanical advantage can be defined as the ratio of the force exerted on a load by a system to the force exerted on the system by the effort. This can be written in the form of an equation as MA equals FL divided by FE, where MA is mechanical advantage, FL is the force exerted on the load by the system, and FE is the force exerted on the system by the effort. If we combine this definition with the principle of conservation of work, we see that in order to have a mechanical advantage greater than 1, the distance moved by the effort when applying a force to a system must be greater than the distance moved by the load. Specifically, the distance moved by the effort must be greater than the distance moved by a load by a factor of the value of the mechanical advantage. This can be stated alternatively as mechanical advantage is equal to the distance moved by the effort in a system divided by the distance moved by the load. This can also be stated in the form of an equation as MA equals DE divided by DL, where MA is mechanical advantage, DE is the distance moved by the effort, and DL is the distance moved by the load. When rescuing a canoe that has been wrapped around a rock, we use a system of pulleys called a Z-drag to reduce the force we need to apply in order to move the canoe. A Z-drag consists of a rope tied to the canoe and threaded through a series of 3 pulleys. The first pulley is attached to an anchor point on shore, which is usually a tree. The second pulley is tied to the rope itself between the canoe and the first pulley. The third pulley is also attached to the anchor point on shore. The pulleys are set up in such a way that when you pull on the rope, the length of rope you pull through the system will always be 3 times the distance moved by the canoe. Another way of stating this is that the distance you move as the effort when you're pulling on the rope will always be 3 times the distance moved by the canoe as the load. We saw earlier that mechanical advantage is equal to the distance moved by the effort divided by the distance moved by the load in a system. In the Z-drag, the distance moved by the effort is 3 times the distance moved by the load, so the mechanical advantage of the z-drag system is 3. We also saw earlier that mechanical advantage is equal to the force exerted on the load by a system divided by the force exerted on the system by the effort. We know that the z-drag has a mechanical advantage of 3, which means that the force exerted on the canoe by the z-drag system must be 3 times the force exerted on the system by the effort, which is the person pulling on the rope. This is how we reduce the force that a person needs to apply to a z-drag system in order to move a canoe. In the rest of the video, I'm going to go over the setup of a z-drag system in more detail, but before we get into that, I want to clear up a common misunderstanding when it comes to the idea of mechanical advantage. Because of the word advantage in mechanical advantage, you may think that you can save energy by using a mechanical advantage system. However, this is not the case. As we discussed before, work is a measure of the change in energy of an object or a system. The principle of conservation of work tells us that in a system where no energy is lost to the environment, the work done on the load must be equal to the work put into the system by the effort. In other words, the energy added to the load in a system is equal to the energy put into the system by the effort. In systems where energy is lost to the environment, the energy added to the load will actually be less than the energy put into the system by the effort. You can see from this that you can never save energy using a mechanical advantage system because the energy added to the load will never be greater than the energy put in by the effort.
So this is a typical z-drag system that I've set up in my apartment stairwell. I'll go through each component of the system and discuss how it contributes to reducing the force necessary to rescue a boat that is wrapped around a rock.
So here we have a loop of rope called a prusik, which is made by tying a figure 8 follow-through knot, as you can see here, in a strand of rope. This loop of rope that we create is then looped many times around the main rope of the z-drag, as you can see here. The function of a prusik is that if you pull on it from this part of the prusik, it causes bends in the main rope of the z-drag here and here, which create extra friction and prevent the prusik loop from sliding along the rope, as you can see here. I can pull and it doesn't slide. However, if I pull here, the main rope of the z-drag remains straight, so the prusik loop can slide along the rope. The next part of the z-drag that's important to discuss is the pulleys that create the mechanical advantage system. So you see one pulley here that's connected to the prusik I just showed you, and when a force is applied to the pulley, it pulls on the prusik from this part, which means that the prusik cannot slide along the rope that it's connected to. This is a very important part of the mechanical advantage system. The pulley I just showed is connected to the prusik that is near the canoe, and the other 2 pulleys that form the mechanical advantage system in a z-drag system are these 2 pulleys here, both of which are connected to this piece of nylon webbing that's connected to my anchor point on shore. Every z-drag system is connected to an anchor point on shore, and it's the rope that is threaded through the 3 pulleys between the canoe and the anchor point that creates a mechanical advantage system. The last component of a z-drag system that's important to its function is this prusik right here. The function of this prusik is that when I pull on my z-drag system, the prusik gets pulled up to this pulley here, and therefore the rope being threaded through the prusik gets straightened out. So when I pull on my Z-drag system, the rope can be threaded through the prusik. But if I let go, then we get some slack in this rope here. The prusik moves down from the pulley just a little bit, and the rope becomes bent at the two ends of the loops in the prusik. This means that the rope can no longer be threaded through the prusik, so I can't lose the progress that I've made in moving my boat. By looking at the pulleys in a mechanical advantage system individually, it is difficult to see how they create mechanical advantage. So now I'm going to show all three pulleys together to demonstrate how they create a mechanical advantage system that reduces the force needed to move a canoe. As you can see in this shot here, on the left side I have the pulley connected to the prusik loop near the canoe, and then on the right side I have my two pulleys connected to an anchor point on shore. This rope right here is the rope at the end of my Z-drag system. If I pull on this rope, you'll see all three ropes in between the canoe and the anchor point are going to move. Since all three ropes move, it means that I have to pull 3 meters on this rope at the end of my Z-drag system to move the canoe 1 meter, which means that the distance moved by the effort, which is me, in this mechanical advantage system is 3 times the distance moved by the load, which is the canoe. This means that the system has a mechanical advantage of 3/1, which is 3. Let's see this system in action. So I'm going to pull on this rope. I see all 3 ropes in between my pulleys at the anchor system, which are here, and my pulley connected to the canoe, which is down here, are going to move. Now let's end the video off with a short clip of a Z-drag system in action on a river.